Welcome back. In this video, I will discuss immobilized biocatalyst and their industrial applications. Immobilization means confinement, just like putting something inside a cage, and biocatalyst is nothing but an enzymes or sometimes a whole cell. So immobilized biocatalysts are isolated or purified microbial enzymes or sometimes whole microbial cells that are confined or localized on a chemically inert support materials, which are called matrix or carrier molecules, thereby allowing their reuse and enhancing their stability and activity. Enzymes are generally immobilized by means of physical and chemical interactions with the matrix in such a way that they retain most of their activity. Unlike chemical catalysts, enzymes are better choice for chemical conversion in terms of industrial perspective. Traditional chemical conversion methods require high temperature, pressure, extreme pH condition and often result in formation of non-specific byproducts. High temperature means higher energy consumption and which increase the cost of production. Additionally, there are problems regarding the disposal of waste materials and that are associated with the chemical conversion process. On the other hand, biological catalysts or enzymes can catalyze the same reaction with great specificity and under normal physiological conditions. And that is the most important part, reducing electricity consumption and sometimes resulting in waste materials that are safe to discard. That leads to green biotechnology. Enzymes are very costly, especially when they are used only one time. When you add the enzymes into the fermentation medium, it will solubilize and at the end it required some additional steps for recovery. Sometimes recovery is also not possible. When enzymes or cells are immobilized, it is easy to separate them from the solution and the immobilization method increase the stability of the enzyme from the external environment and they can be reused for multiple times and hence reduce the cost of production. The cell immobilization has been exploited long before it became recognized as potential valuable technique in terms of bioprocess engineering. Before industrialization, cells were immobilized in soil, charcoal, wood shavings. As you all know, immobilized cells are used in wastewater treatment and vinegar production. In 1960, single enzyme immobilization was first used for the production of amino acid and for the isomerization of glucose. And this method became popular and after that several enzyme immobilization techniques are gradually developed in between 1985 to 1995. The main component of enzyme immobilization are the enzyme itself and the support materials. The efficacy of the enzyme depends on how they interact with the support material. An ideal support material should be hydrophobic, do not react with the enzyme, resistant to microbial degradation and can be reused, and the most important of all, that is the cost. It should be durable, biocompatible and efficient. Support can be classified based on their chemical composition into organic or inorganic types, which further divided into natural and synthetic polymers. Among the commonly utilized support materials for enzyme immobilization are carboxymethyl cellulose, starch, collagens, modified saccharose, ion exchange resin, activated charcoal, silica, clay, etc. And the list provides a comprehensive overview of the carrier materials that are commonly employed in enzyme immobilization process. There are several methods for enzyme immobilization applied in industries. These techniques can be divided into two types based on the interactions between the enzyme and the support materials. If the enzyme and the support material formed a chemical bond like covalent bond, they are classified as chemical methods of immobilization and due to the covalent bond formation, enzymes are attached onto the carrier molecule very strongly. And as a result, it is hard to detach the enzyme from the carrier. And for this reason, this type of immobilization is called irreversible immobilization. And in physical methods, no covalent bonds are formed between carrier molecules and enzymes, and only some weak non-covalent interactions are responsible for the binding, and therefore it is reversible. Each of these methods has its advantages and disadvantages, and the choice of immobilization method depends on their application. This method is very simple and inexpensive, and generally surface active absorbents are used as a carrier, And in this method, enzyme solution is mixed with the absorbent material under appropriate conditions like pH, temperature, ionic strength of the solution. And after a particular time, the unbound enzymes are washed out. Mainly weak non-covalent interactions like salt bridge, van der Waals force are responsible for the attachment. This method is very easy and cost effective, and high enzyme loading is possible. And here the chance is very minimum that the essential amino acids responsible for the enzyme activity are involved in the bond formation. When the shelf life of the enzyme is lost after the use for several times, the separation of the enzyme is also very easy by altering the chemical environment, and therefore some absorbent material can be reused. Coconut fiber, cellulose, even mesoporous silica nanoparticles are generally used as a support materials. The main problem is that the enzymes are bounded via weak interactions, so they can be washed off very easily. All the interactions are pH and temperature dependent, and that limit their use in a wide range of catalytic reactions. As depicted in this image, the enzyme interacts with the carrier material, possibly through ionic or van der Waals interactions, with no specific amino acids from the active site involved in the attachment process. The enzyme maintains its activity. However, as the environmental pH shifts due to increasing substrate concentration in the fermenter or because of the accumulation of the end product, the enzyme begins to detach from the carrier molecules. Packaging of the enzyme inside a tiny spherical capsule ranging from 5 to 300 micron in diameter in semi-permeable or liquid membrane is called microencapsulation. Generally, in membrane confinement method includes formulation of liposome or microcapsule. To prepare microcapsules, a concentrated aqueous solution of the enzyme is first prepared. The aqueous enzyme solution is then emulsified in an organic solvent or solvent with a surfactant which is soluble in the organic solvent. The emulsion is stirred vigorously, and because of that, small droplets are generated and enzymes are trapped inside it. The semi-permeable membrane is allowed to harden around the microdroplets, and the microcapsules are then washed and then transferred. More commonly used membrane are cellulose nitrate and polystyrene or nylon. Because of their small size, the surface area is increased significantly. Depending on the nature of the membrane, only some molecule can diffuse that greatly increase the specificity of the end product. This method has several limitations also. Only small molecule can pass through, and the leakage of the membrane can also occur, and as a result we will lose some enzymes. The shear force applied during droplet formation can damage the enzymes also. The entrapment of enzyme, no reactions are occurred between support and the enzymes. A cross-linking polymeric network is formed around the enzyme. In this method, a suitable gel or fiber are used for the physical enclosure of the enzymes. Due to the porous nature of the carrier molecules, substrate and products can easily diffuse in and out of the matrix, but the enzymes can't. Polymeric materials like calcium, alginate, agar, polyacrylamide, and collagens are used more commonly for enzyme immobilization. Not only that, some active materials like activated charcoal, activated carbon, porous ceramics, and diatomous earth can also be used for this purpose. The main criteria of the matrix is that it should be composed of particles, membranes, or fibers. The main advantages of the physical entrapment are as follows. The process is very simple. The enzyme solution is mixed with the reagents during the time of polymerization. The small amount of enzyme are used in this technique. The structure and activity of the enzymes are not altered because no chemical bonds are formed, and water-insoluble enzymes can also be used in this method. The disadvantages include the leakage of the enzymes and some chemicals into the solution. If the enzymes are enclosed, they can't able to move, and as a result the collision between enzyme and substrate are also minimized, and the rate is also altered, and sometimes the substrate enter inside the matrix but the product can't able to escape in case of large macromolecules. For example, in this case the substrate is a monomer but the product is a polymer, and due to the polymerization the size of the product is increased and that trapped inside the gel matrix. Sometimes thermal damage can occur in the enzymes during the gel formation. This is the most widely used method for enzyme mobilization. The enzymes are covalently attached onto the surface of the carrier molecules, and the attachment is stronger than physical attachment. The covalent linkage is achieved between a functional group of the enzyme that is not located inside the active site or any other regulatory sites, and a reactive group present on the surface of the support material. Generally, amino group, carboxyl group, hydroxyl group, indole groups are involved in the covalent bond formation. Lysine is the most preferred amino acid of the enzyme for covalent bond formation. Some commonly used support materials are synthetic and natural type. They are listed in this table. You can check example of each also, and sometimes the functional group of the carrier molecules are activated using cyanogen bromide or glutaraldehyde. The main advantage of the covalent binding method is the strong binding, and hence there is no enzyme loss while immobilized enzyme are used. The enzyme support derivative is easy to manipulate due to the great physical and chemical variation in the available support materials. The most of the supports are widely available commercially. However, this method has several disadvantages. Some preparation can be quite tedious to execute. Chemical bonding may lead to enzyme inactivation or alteration of the shape in certain cases. For instance, a lysine residue, crucial for the enzyme activity, may participate in bond formation and resulting in enzyme deactivation. The reagents involved in covalent binding can further increase the cost of immobilization procedure. Since carrier molecules can't be reused, the ratio of carrier and enzyme is typically very low. In this scenario, the enzyme will attach only where the charged molecule are present, thus resulting in lower loading compared to physical attachment. This method involves attaching biocatalysts to each other using bi or multifunctional reagents or ligands. This process results in the formation of typical insoluble aggregates of enzymes like this that has a very high molecular weight. Cross-linking is a relatively straightforward process where enzyme molecules are immobilized by creating bonds between them and through the use of polyfunctional reagents. These reagents react with the enzyme molecule, forming a bridge that serves as the backbone to hold all the enzyme molecules together. Several reagents are commonly used for cross-linking. You can find some of their names from this table. Glutaraldehyde is the most extensively used cross-linking reagent. It reacts with the lysine residue of the enzymes. The cross-link formation between the enzyme and glutaraldehyde is irreversible and can't withstand extreme pH and temperature conditions. Glutaraldehyde cross-linking has been successfully used to immobilize several industrial enzymes like glucose isomerase and penicillin amidase. The technique of cross-linking is relatively simple and cost-effective. However, a disadvantage is the risk of enzyme denaturation by the polyfunctional reagent. Immobilization technology has had a very profound impact on microbial fermentation technology, enhancing their yield of fermentation-based products such as organic acid, antibiotics, enzymes, bioethanol, and as well as in facilitating biotransformation. Furthermore, immobilization technology has been widely utilized in the advancement of biosensor, utilizing both whole cells and pure enzymes. That concludes our discussion for now. If you enjoyed this video, please consider liking and subscribing to my channel for more content. And don't forget to visit the community page for multiple choice questions. And lastly, thank you for watching.